So we'll just continue from last time in dense matrix or dense graph algorithms, but I have a couple of announcements. So this is just copied from a post on Ed, but I will also post it on Canvas. So we have a final exam in a little bit less than 2 weeks, assigned by they have a matrix of the times. And I put the exact time on the next slide, but this first one is the topics. So it will be everything besides MPI. And so for the first exam, as a reminder, we had efficiency and speed up, and scalability, work span analysis for multi-threading, cache complexity and cache oblivious algorithms, and prefix sums. And then for the second exam, we had communication primitives, sorting, like Pythonic sort and sample sort, embeddings, dense matrix algorithms. And then after the second exam, we had FFTs and body simulation, interconnect networks, sparse matrix vector, and dense graph algorithms, which we will finish today. So we have I think we have 3 lectures left, counting today. So the next 2 will be regular, just on the remaining topics, and next Monday we have 1 more class, but there will be no assigned lecture. If you have any questions, I'll just come here, and then if you have any questions, you can come ask me. So, any questions on the topics?
Will the rest of the semester just be more dense graphs, and then is that covered by?
Oh yes, so today we'll probably finish dense graphs, and then we have 1 more real lecture Wednesday, so I'll talk about sparse graph algorithms. You'll see, like when we talk about it, it's a bit hard to make a question about it, so it probably won't be on the exam, but I think it's interesting, and we have time, so yeah, that's what's gonna happen. Yes. I'll try to make it about even, so like 1/3 in the first third, 1/3 in the second third, 1/3. It probably won't be exactly even because the number of questions may not be multiple of 3, and the number of questions will probably not equal to the number of bullet points here. So, but I'll try to make it about even as possible. In terms of the length, so the length will probably be about 1.5 times the regular exam, but the time is more than 1.5 times. So I will cover it in the next slide. Any questions? We'll talk about logistics in the next one. But just for now, on the topics. Will there be emphasis on the materials that we haven't been tested on? No, it'll be about even. So, like 2/3 in the stuff that you have been tested on, and 1/3 in the stuff that you have not been tested on. But the stuff that is not yet tested will mostly stick to the stuff in the homeworks. So, like probably not sparse matrix algorithms. I'll talk about it a little bit in the next, like which ones of these are easier to make long form questions on. So I'm going to go to logistics, but if any questions come up later about the topics, you can also feel free to bring them up. So going back to this question about like the last third, the long form questions, they will probably mostly relate to, if you look at the practice exams that I posted on Canvas, the long form questions are mostly related to FFT and interconnects or graph algorithms. So this is also already on Ed, and I just copied it for the Ed post, and this will also be posted on Canvas. So, like there may be short questions, like we had before the true-false, about the other topics, such as n-body simulation, or later on we'll have sparse graphs, but it's a bit harder to make long-form questions about those. So, like if you look at the practice exams or the homework for interconnect, for example, one really easy one is like draw the omega network on 8 processors and route some permutation through it. Whereas it is a bit more challenging to write a long-form question at the same level for n-body simulation, for example. So yeah, hopefully that answers your question about the last bit of the topics. And for those, you can check the homeworks, and after the homework 7 comes in, I will post the answer for that as well, so you can study that, and the practice finals on Canvas. Also in terms of long form questions, since this is comprehensive, it may cover more than one of the topics. So for example, dense graphs, and those, you can see that they're very related to dense matrix algorithms. And so it's hard to talk about dense graphs without talking about dense matrix problems. And for example, like part of it, you may have an algorithm and you may be asked, for example, like what is the speed up or the efficiency? So relating to earlier topics as well. Even if the topic itself is about dense matrix problems, for example. And yeah, in terms of just the actual day of logistics, it's the same as before. You can have one regular group sheet. This is the time assigned to us by the matrix. Unfortunately, it is at 8 a.m., so there's nothing I can do about that, sorry. And yeah, it's next Friday, just here. And yeah, like I said, the practice exams are on Canvas, just in the same normal place, so like files, practice exam, there's a finals folder. Any questions? Yeah, so you can have this whole time. It's almost 3 hours. And so earlier we were talking about the length. So the normal time length is 75 minutes, which is 1 hour and 15. If you double that, that would be 2 hours and 30. This is 2 hours and 50, and the length will not be double of the exam. So like in previous exams, we had about 5 questions. Length will probably be somewhere between 7 and 8. I'll shoot for 7 and 8, between 7 to 8 questions. So the length is about 1.5 times, and the time is more than 2 times. So the time per question is longer. Questions, concerns?
We consider that two cheat sheets is unfair like one
You can have 2 sides of one cheat sheet.
yeah, and we consider that one more cheat sheet.
Oh, no, sorry. Can you bring a calculator? No, you won't need a calculator. But if you didn't know how to convert between binary and decimal for last time, then it's something that you should probably learn for this time. But like in terms of the actual calculations, it's nothing so complicated to make a calculator. Other questions? Yeah, so when you look through the final exams, if you have any questions, feel free to ask them in the office hours or post on Ed. And yeah, actual format, like, so as before, in the practice exams, I had them from the previous years, and everybody has a different style of how they format the question. So the format will be similar to the previous exams that we had, but the content will be the same as the exams from last year and the topics from the lecture. Any questions? Yeah, if anything comes up, feel free to ask about this. Yeah, last thing, the science I think is open today. I'm trying this time, we'll see how it goes. So I've seen examples, but we're gonna do it. So there's 2 sections. We have the grad section and the undergrad section. I will also post this on Canvas, the 6220 and 4220. I won't see, like they close on May 4th, which is after we have finished the final exam and everything. And yeah, so I can only see the percentage of reply, and if we have, but this is before the final grades are due, so I can just apply this. If we have more than 75% reply in any of the sections, it will apply to that section. Or yeah, so like they'll apply separately to the different sections, but there are 2 sections, and the sections are graded separately. 75% plus 1, and then 85% or more is plus 2. It's not cumulative. It's not like if it's 85%, it's plus 3. It's like the max of the 2. Any questions about this? This is pretty common in other classes. Yeah. We appreciate any feedback. this is my second time teaching this class, so it's still pretty new for me, and I'd be happy to hear feedback about the topics or assignments or anything. Thank you. Cool. So if there are no questions about that, we are going to move on back to dense graph algorithms. So last time we were talking about Prim's algorithm for minimum spanning tree, and this was the pseudocode. The high level of how it works is that you have a vector of distances, and you start with an arbitrary vertex, and in the beginning, the vector is just the adjacencies of that vertex, and you add in vertices one by one iteratively, and you update the spanning tree based on that. And the vertices that you add in must be connected to the current spanning tree. So this is the pseudocode. First, we start from some arbitrary vertex R, and this is the vertex set in the tree to begin. So in the beginning, it only has one vertex in there. And in the beginning, if there's some edge from the start vertex R to some outer vertex V, then you set distance of V, this is some distance vector, to the weight of R to V. So that's just the edge weight. If they're not connected, that's infinity. And while there's still vertices in the vertex set, this is the set of all vertices V, we take them in over the distance vector. So at any point in this iteration, D, this distance vector, contains the distance between, the minimum distance between anything in the spanning tree currently to anything outside the spanning tree. And then in the next step, we take, just in a greedy way, you take the closest one that is currently outside the spanning tree and add it into the spanning tree. And then you have to update the distance vector because now we've added in a new vertex, so we have to take in those new adjacencies, and that's what this is. So we pick the new U, which is the vertex to add in. We need it into this set of vertices in the tree, and then for everything that's not in the tree, we take the minimum of the current distance and the new distance that we have updated in. And last time we said that these parts are easy to parallelize, so updating this is only just taking the row in the adjacency matrix and copying it in to the distance vector. That's just initialization. The second one that's easy to parallelize, we know how to take min over a vector in parallel. The same as sum, but with a different operator. And then this one is also independent, so that for all vertices, we take the element-wise min of what is currently in the distance vector and the weight UV, which is something in the row U and column V in the matrix. And those are all independent because you can parallelize over V. Any questions? The direction that we're going to go clear? So you can see that dense graphs and dense matrices, well, not just dense, graphs and matrices are very related because we store the graph structure in the adjacency matrix, and we're just taking min over rows, basically. And we're doing element-wise comparison in rows. So when we parallelize this is how it's going to go. We have P processors. This distance vector has n entries in it, one for every vertex, and this adjacency matrix has n squared entries in it. So every entry UV is the weight from U to V. And we can just partition it like this. So we cut this up into P pieces, and we cut this up into P pieces like this way, where the pieces are distributed 0, 1, that are up to P minus 1. And so the reason that we're doing the partitioning this way is if you remember the main steps that we have to do. The first step is taking the min over this distance vector to find the new vertex that we add in the next iteration of the MST. And the second step is once we identify the new vertex to add, you take the row. So let's say we take some row or some new vertex U, which corresponds to this row. We're taking the element-wise min of this section and this section, this section and this section. So for the actual updating of the distance vector, there's no additional communication between the processors because this piece and this piece both live on processor 0. So the only part that needs communication is the min in the distance vector. The part of the graph that you need to go to the new iteration is already on the correct processor. Okay, this is just the analysis part. So there are n rounds, because in each round we add in one new vertex, and there are n vertices. So the first step is that we have to identify the new min, or the new vertex that we're going to add in. So we take the reduction with min operator over the distance vector. It has length n, and there are p processors. So we just plug in to the bound that we had for reduce, which is this. For n items and p processors, the computation is n over p plus log p. Oh yeah, I will also give the same table, the same sheet of bounds on the exam that we had last time. Just copy it. So you don't have to remember this. And the communication time is tau plus mu quantity times log p, because the reduction is height log p, and each level of the reduction takes tau plus mu size, and it's just reducing one element in every run, or in every level. So you can reduce, which is you take the min, and then you could broadcast. Both steps could be replaced with one all reduce as well, because everybody needs to know the new vertex that we bring in to the MST. So you could do a reduce, then a broadcast, or you can just do an all reduce. And then we'll find out who is the new vertex to add in. Then once we find that out, you can update the distance vector. And that takes no communication, just takes n over p time computation, because we compare one piece of a row in the adjacency matrix with one section in the distance vector. So that's just element-wise comparison of n over p elements. So if you combine them, so that's the whole algorithm, that's one step. And then you repeat that whole thing n times, which is where we get this total time. So if you multiply by n, this thing, plus this thing, you will get order n squared over p plus n log p. This is smaller than this, so it just goes away in the big O. Like 2 n over p is order n over p. And multiplying the communication time also by n is just tau plus mu log p times n. Questions? So, like I said last time, this is nothing new, in that we know the communication primitives, we know about dense matrices, so we're just putting the pieces together to make new algorithms. And it's efficient. We have seen forms like this. This is efficient up to order n over log n processors. Questions? So that was minimum spanning tree, one algorithm for MST. Now we're just going to do a few more examples of graph algorithms. So single source shortest paths is another common graph algorithm that people may be interested in running. The formulation is like this. We have a graph, V, E, and W. So V is the vertex set, E is the edge set, and W is the weight function. And single source shortest paths is given a source vertex, you want to find the shortest path between that source vertex and all the other vertices in the graph. And the most famous algorithm to compute, so single source shortest paths is SSSP. And the most famous algorithm to compute SSSP is Dijkstra's algorithm, which works on basically this iterative edge relaxation. And the way it works is that you start with your source vertex, you look at the adjacencies of the source vertex, and then now you have computed the shortest path between the source and things that are one hop away, considering one edge. And you keep adding in vertices. This is the pseudocode for Dijkstra's algorithm. Do people already know Dijkstra's algorithm? Does anybody not know Dijkstra's algorithm? So in terms of the signal code, it looks actually extremely similar to Prim's algorithm for MST. So we start with some source vertex in the vertex set. Now we call it S, but it doesn't matter what it's called. And this part is initialization. So while for all the vertices that are not the source, the current distance is just the weight of source to V. So this is all the things that are immediately adjacent to S. Otherwise, if they're not adjacent, we set it to infinity. So now, this is called L now rather than D. This is called S now rather than R, I guess it was last time. But this is exactly the same setup as we had in Prim's algorithm. And so now this is the iterative part. While the vertex set for the V sub t is not equal to the whole vertex set, go like this. We take the min over the current L vector, such that the min over the L vector is the smallest one. So this is the smallest distance currently outgoing, such that it's not yet visited. And then we add that in to the vertex set. And for all things that are not yet added in, we do this relaxation step. You take the min of what is currently in the L vector with what is currently there plus the weight of VB. And the way to understand this is, so currently this is the LV is the distance from S to V. And the shortest path can either be what is currently, we have the shortest path, or if we add in this new vertex U, it is the path from S to U plus the distance from U to V. So you can get a new shortest path through the new vertex that you have added, or maybe it doesn't update the shortest path. And that's this relaxation. And so this is pretty much the same as Prim's algorithm, except with a tiny bit of change in this operation. Before Prim's algorithm, it was just min between the vector and the weight. Now it's just min of the vector and the vector plus something. So since the structure is the same, we can also parallelize it in the same way. So Dijkstra's algorithm is very similar to Prim's algorithm in terms of high-level flow for MST. And so we can partition the vector and the UGC matrix in the same way. And we partition it using this 1D mapping. So we cut the distance vector, p pieces, and you cut the matrix also in p pieces. Each piece is n squared over p, because the whole thing is size n squared. And the high-level iterative flow is exactly the same. You find, in each step, you have to find the min over the distance vector, and everybody has to know that min. And then you either find, you can find a new shortest path by taking into account the new vertex and like the path that goes through the new vertex. Questions? So again, this is even less new because it's just pretty much the same as Prim's algorithm, but we're gonna try to use it in bigger problems. So finally, the last problem that we're going to do for dense matrix problems is all pair shortest paths. And all pair shortest paths is just like an extension of single source shortest paths. So for single source shortest paths, it was from one start vertex, S. But now for all pair shortest paths, you want the shortest path from any pair of vertices, U to V, in the graph. And if you have an algorithm for SSSP, you can solve APSP by just running your algorithm for SSSP from every vertex. And then you would, since the formulation of APSP is just give me the shortest path from any vertex to any other vertex, and SSSP gives you the shortest path from some vertex to all the other vertices, you just run it. So you would trivially have a solution for any of them. And like, given that we just had an algorithm, Dijkstra's algorithm for SSP, we could just run it from all the sources. But there are other ways to solve APSP as well. So we have a bunch of algorithms. The first one, as you may be very familiar with now, is based on matrix multiplication. The second one, like I said, Dijkstra's algorithm. You just run it from all the sources. And the last one that we'll talk about today is Floyd's algorithm based on dynamic programming. So for the matrix multiplication based one, if you have an algorithm for matrix multiplication, you can also trivially solve APSP by doing repeated multiplication. But you don't do it with the initial, if you have regular matrix multiplication, you do the dot product with plus and multiply. I guess you already may know this from the homework, but you do it rather with plus and min. Because, so the actual meaning of plus and min is that if you have the adjacency matrix, and you square the adjacency matrix, each row is the distance from u to v, for all v, for some given u. And each column is the incoming distances. So v is the up. So like if your column is v, this is all the edges that come into v from all u. And so if you multiply them, if you multiply some row u and some column v, that's all the two-hop distances from row u, from vertex u, to vertex v, through some intermediate vertex. So that's one matrix multiplication, because matrix multiplication does every row and every column. So after one squaring of the adjacency matrix, every entry is the two-hop distance between any vertex and any other vertex by changing the operator. That part may not be super obvious, so there may be questions. Not really, I guess. In some sense, dynamic programming from like Floyd's algorithm, you start, like the recurrence starts from k, where k is the maximum min, and goes down to 1. But here, in some sense, with repeated squaring, you start from 1, 2, 4, and go up to n. So I would say it's just going the opposite direction. But the actual meaning is the same of the intermediate path. Good question. So maybe I can go through this in a different way, which is that, say you have one row, so you have two copies of your adjacency matrix, and you multiply them together using this form, which is you do one row and one column dot product, but you do addition, and then the way you combine them is through min. So addition is adding up two edge distances between source and the final destination with one intermediate vertex. And min is taking the min over those two hop paths. So from one row and one column in the multiplication, adding them is just adding up like the two edges between, going through any vertex between them. And then taking the min over all of those is the min over all the two hop paths between any given vertices. And if you repeat that, so that's what happens if you square it. But then if you do it again, then you would, on the square that you just computed, then you would have distance 4. If you compute it again, you have distance 8, and so on like that. And then, so from there, if you took a to the nth power, you would have all distance n paths.
should just like observe that there's nothing left that is, I don't know, I think the algorithm, I don't know. And I'm not articulating it, but
Maybe my understanding of the question is like,
Yeah.
how does this work for non-power 2 links?
yeah, that's what I'm saying.
Yes, good. I will have a slide on that in a moment.
Oh,
But before we go there, are there any questions on this? So you could do this by just, you keep multiplying a times a times a times a, which would take you n matrix multiplications. But ideally, we would like to do it in something like log n multiplications. And if n was a power of 2, then this would be easy, because you would just keep repeated squaring. So you would have 1, then 2, then 4, then 8, and so on, up to whatever power of 2 you want, and that takes log n multiplications. Okay, and this is just an example. So this is your graph, this is your JDC matrix, and a to the 1 is just the initial input. A squared is the 2 hop distances, A4 is 4 hop distances, A8 is 8 hop distances. And so, what if you have a non-power 2 number of vertices? Well, in the intermediate multiplications, you will have computed all powers of 2 up to maybe one less than your actual number. And then, because any number can be represented in binary, you could think of any of those repeated multiplications, or squares, as one bit in the binary representation. So for example, if you had n equal to 5, you can write that as 101, which is like 1, 2, 4, because the meaning of the binary bit is like increasing in powers of 2 from right to left. And then so you could get power a to the 5 by multiplying a to the power 4 with a. And you can get any arbitrary number by multiplying at most log n intermediate multiplications together. So that's why you shouldn't just keep multiplying up to n, because then the number of iterations is proportional to n rather than log n. Does that answer your question?
It was also, I guess maybe it's not understanding, like why do we need to save a and a to the 4th at all? Like once you go past it, won't the algorithm just see that it can't add any more vertices or edges, and then just give you the result of for 5, or?
Oh, like if you had a to the 4 and you just tried again to go to like a to the 8.
Yeah, and then like suppose there's no path that's like of length 8, right? Would it just give me like a to the 5 if 5 is the longest path?
So because a to the 8 would be a to the 4 times a to the 4, and then so like a to the 4 is all paths of length 4, so you're trying to concatenate
Oh,
paths of
right.
length 4 together if you multiply them.
Okay.
Yeah, good question. It's a little bit subtle. Questions on this part? So in linear algebra terms, they call changing the operator changing the semi-ring. So if you ever read any paper where they talk about changing the semi-ring, that's what that is. Using building blocks from linear algebra to express graph algorithms. And the reason that we're interested in is in this way because we often have highly optimized routines for matrix multiplication, like sparse matrix or dense matrix. So if you want to express your graph algorithms with basically no extra cost, you can just plug in whatever routine you have for matrix multiplication. So we can compute a to the n, which is going to contain all shortest paths, by doubling the powers. So a to the power 1 is the beginning, then a squared, e to the power 4, e to the power 8, so on. That is going to take order n, or order log n, sorry, matrix multiplication. multiplication, each time is order n cubed for one matrix multiplication. So the total serial time would be n cubed, order n cubed log n, because each one is n cubed, and you're going to do at most log n of them. And it's not optimal because, it's not work optimal because Dijkstra's algorithm takes time order n squared in serial. And if you run it n times, like we were just saying, you just copy it n times, that would take n cubed. But nevertheless, it's good to know that you can do this, because if you don't have like a fast implementation of Dijkstra's algorithm, but you do have a fast implementation of matrix multiplication, you can easily implement operator response already. Oh. Okay, so you're saying, for example, if you want the 10 hop path length, you would have to multiply A8 with A2. Yes, the claim is that by the time you have AN, it's not exactly like distance n paths, exactly distance n paths. It's like, it's sort of the reverse of Floyd's algorithm, if you know Floyd's algorithm, which is at most length n paths. Just how, like a squared is kind of like at most distance 2 paths. Because if you take them in Floyd's algorithm, or in like even a squaring, and it turns out that the min in that row was just distance 1, that would be a valid path. And so the total serial time is n cubed log n. And if you plug in any matrix multiplication, any parallel matrix multiplication algorithm, somehow the APSP time will just fall out because you multiply what we had for matrix multiplication, the whole thing by log n. So using Cannon's algorithm had computation time n cubed over p, and we're just going to multiply that by log n, because there are log n rounds. And then on the other side, for communication, Cannon's algorithm had this communication time tau root p plus mu n squared over root p. Multiply the whole thing by the number of rounds, which is log n. And like I was saying earlier, it's not efficient with respect to the best serial algorithm, because we know that we could get a serial algorithm that takes time n cubed, but it is efficient with respect to the serial algorithm for some, this is not a small number of processes, order n squared. N squared is likely to be greater than the number of processes you have in most practical cases. So that's why this is still a useful formulation. So these are just examples of how you can just plug in matrix algorithms that we already have to get graph algorithms for free, in some sense, with pretty much no additional programming effort. So that's one way to do it. Another way is, what I was saying earlier, we have Dijkstra's algorithm. You could just run it from all the sources, and you would have a solution to APSP. That would take in serial n cubed, because one run of Dijkstra's algorithm takes time n squared, and so n runs of it would take time n cubed. So there's two levels that we can do the parallelization. One is that we have n separate copies of the problem, and if we had fewer than n processors, or if we had at most n processors, we could just run the separate copies on the different processors, and we wouldn't even need to do any parallelization, because that would be problems like this. They're called like pleasingly parallel. they're trying to move towards that. They used to be called embarrassingly parallel, which is that you don't need to do any thinking about like how to do the partitioning or work distribution or anything. You just have separate problems and you can run them separately. So you have n copies of the shortest path algorithm, and you can run it on up to n processes, assuming that every process can hold the adjacency matrix. And then if you have more processors, then you can use the parallel formulation that we had earlier, where you cut up according to the 1D block decomposition. And that would increase the number of processors that can be used up to n processors as well, because each one of those was cutting by columns, and so you have at most n columns in each one. So total, you could use up to n squared processors. So we would start with the easiest way to do the parallelization. If you have up to n processors, you just copy it. Each source is on a different processor. And this requires no communication between them, because each of them is running a different problem. And so the parallel runtime, assuming that you have something like n processors, would be n squared, because each of them can run in parallel, and each problem takes time, serial time n squared. And that's efficient up to n processors. And then the second step is if you have more than n processors, then we can do the parallel formulation that we had earlier of one copy of Dijkstra's algorithm, which is that we cut up along the columns and the distance vector. And given some p processors with p greater than n, each single instance would be executed by p over n processors, because you have p processors and n copies of the problem. So plugging p over n into what we had earlier, we can get out the computation time and the communication time. So the computation is like this. We had to do this broadcast step. We had to do, this like all reduce, broadcast reduce type step to find the new min in every round. That's where this log p comes from. And then the communication time is there are n rounds, and then the reduction takes log p. And that's efficient up to n squared over log n processors. So this is the last part of dense graph algorithms, which is Floyd's algorithm for all virtuous paths. So this is the same as you were saying earlier about dynamic programming. And Floyd's algorithm is the dynamic programming algorithm over the intermediate vertices. So for any pair of vertices, I and j, basically what is going to happen is that we're going to consider every intermediate path from v sub I to v sub j, where the intermediate vertices are in this set, v sub 1, v sub 2, up to v sub k. The dynamic programming works on k. And we have this p sub ij super k, which is given some weight, corresponding weight with the same sub and the same indices. So p is the path, and d is the distance corresponding to that path. And ij is the vertices that the path is between, and vice versa, that the distance is between. And k up here is in some sense like the step of the dynamic program that we're on. So the dynamic program works like this. You have some vertex vk, and if it's not in the shortest path between these two things, then p sub ij with the kth step is the same as excluding it, which is p to the k minus 1 ij. then so there are two cases. The first one was if it's not in the if this v sub k is not in the shortest path, then it's just equal to the previous step of the dynamic program that does not include it. Otherwise, if it is in the shortest paths, then you can break the shortest path in the kth step into two, one from I to k and one from k to j. And then each of those two paths should use the vertices in the previous dynamic programming step. Who's familiar? Let's see if there's anyone. So it follows this recurrence. So you start from, the base case is k equals to 0, and you start from the superscript being k, and you go down k minus 1 in the recurrence tree. And so this distance, ij, so this is the thing that we're trying to figure out in the end for all pairs ij, because k ranges from 1 to n. And if k is equal to 0, then the distance is just the weight from vertex I to vertex j. And if otherwise, if k is greater than 1, then this expresses the recurrence that I was talking about earlier, which is either k is not included in the shortest path, and so it's just equal. This is the distance excluding k, so you just take the iteration superscript of k minus 1. And then this is the second case, which is it does go through k, and so that you can break it down into two paths, ik and kj, including vertices 1 up to k minus 1. So these are the two cases on the previous line, and you take the min between them to find the shortest path, including vertex k. So this is, earlier we were talking about how does this relate to the matrix multiplication. In some sense, like this is going from k down to 1. The matrix multiplication is going 1 up to n. But k starts at n, just like n down to 1 and then 1 up to n. And to write this serially is actually just very few lines of code. Start with some distance. So in the end, you're computing a matrix. For all pair shortest paths from, you're computing a matrix where the end result of the matrix, every row column is the shortest path distance from that vertex to the other vertex. So you start with the initial matrix A, which is the adjacency matrix, and we run these through loops. 1 up to n. K is the outermost loop, which is the dynamic programming, the DP variable. And I and j are the indices in the matrix. And so every round of k just does this thing, which is for every entry in the matrix, compute the next step, which is the min of the previous, the min of, this is the previous path that we had found, or the other case, which is that you combine the two paths through the intermediate vertex. So we could parallelize this by, we just put a parallel 4 on this thing and this thing, assuming that you can keep around dk minus 1. This is just every entry of dk just depends on these. It doesn't depend on any other thing. It doesn't depend on like any more intermediate things that you're computing for dk. It just depends on dk minus 1. So you could parallelize over all the entries. I had a problem like this in the homework a long time ago. This is also similar to matrix multiplication. Like matrix multiplication in the most simple way has 3 loops at jk, and you can reorder them any way you like. So how would you divide the matrix onto P processors to parallelize this?
Well, I guess because we can parallelize the inner loops, we could just do a 2D decomposition.
Yes. Yes, good, exactly. So, does that make sense? Are there any questions about that? We're going to use 2D decomposition of the matrix to compute every tile. Yeah. So we have this one matrix d to the power k. We're going to, if we have a root p by root p grid for a total of p processors, we're just going to cut it in the same way that you usually cut the 2D matrix, n over root p by n over root p. So total size for each one would be n squared over p. And each processor updates, so every processor is computing its square of d to the power k in the end. And so what does it need to compute in each step? Well, for k, it needs, so for every path, I guess this is LR, left, right, maybe, processor Pij, to compute the tile Dij, it needs, in the kth iteration, the path from L to k and the path from k to r to compute the intermediate, to compute like the min for the dp. And so what does this mean in the matrix? This is column k, this is row k for all r and all l. Actually, this kind of looks a lot like Summa, in the sense that in every step, we're going to broadcast one row and one column. But in Summa, you broadcast like the block row and the block column. But here, for every step, you just need one whole row and one whole column. With this is column k, because k is fixed, and L is ranging over all L, which is like the incoming vertex. And then here, the row is k, and R is ranging for all the outgoing end vertex. So during the kth iteration, you broadcast the kth row and the kth column, whoever has it, along. So you broadcast the row along the relevant processor column, and you broadcast the column along the relevant processor rows. So this is just a picture of the 2D decomposition. It's not super important about the exact indices. And then this is the broadcast way. So say that we are on this row and this column. Then to compute DLR, we need DLK and DKR to take them in for the next step of the DP. So we take them in with what we have already, d to the power k minus 1, which is already on this processor, and we need to get in d to the power k minus 1 of the path from L to k, and d to the k minus 1 of the path from k to r, which is, for this one, is in this row, and for this one is in this column. And so in every step, we first do this broadcast, and then everybody now has what they need, and they can independently take them in with the previous step of their DB. So the actual steps are very close to the Summa algorithm. Like, you do this broadcast, then you do some local computation, and you repeat it for as many rows / columns as you have. And this is pseudocode. So the outer loop is over k from 1 up to n. The inner loop is you broadcast, so k is the fixed variable in this round. We broadcast the kth row along the column. Yeah, you broadcast the kth row along the column, like each segment. And then you broadcast the kth column along each processor row, the relevant segment of that. And then each processor gets the segments. And finally, each processor has what it needs to compute its portion of the matrix in the next, to compute d to the power k for the next round of the DP. And that's it. You just repeat it. So what is the runtime of these broadcasts?
It's